Scala. To run this, you can open the command line editor, cmd.exe, and then just say Scala tutorial 6 Scala. Okay, this one will contain from the errors. Wait, actually there's no errors, but because we haven't filled in anything, so it's not actually run. This one doesn't actually run anything. Okay, so the first question. So have you done this before? You know, Camel or Haskell to get the last element. So how do you get last element? If the list is empty, then you actually overshoot, right? So you need to have the cases where it's not actually at the end yet. Because if it's at the end, so you can either use nil here, or you can use list empty. So both are the same because nil is just it's the same. So if you do this, okay, so this one is an error, so you just throw a new exception saying that there will be an error. If it is not the last element, so somewhere in the middle, then you just have to recursively go inside the game. You look at the XS. So just say last XS. Okay, but if you keep on doing this, eventually you will reach the nil. So how do we prevent that? There must be one more thing before here. And the other thing before this is basically the case where you have X followed by a nil. You are the very last element before the list is empty. Right, so for this particular one, then you say, well, the answer is definitely just X. Okay, so this one is just X. If you still have a lot more, then you just continue on with the rest of the list. Okay, so here if you want to test, so we'll be testing Q1 running. Okay. The S here is not part of the output, is deprecation for details. It's the first input is this 3. Okay. So 3 and 1. So if you try this one, then you will get the error. Okay, so if you uncomment this, if you start with an empty list, then you will only match with this particular case. So that will give you an error. Okay, the error is quite long. So if you look at the top, no last element. Okay. The reason why there's a long list of this is because we do a recursive call, so it needs to print out all the trace. Right, so any questions on this? Yeah, wrong. This one. Okay, so is it clear? So if your empty list is definitely an error. If you are still having a long list, then you just go to the rest of the list. But if you are at the last element, then just return that particular last element. So what is the type of this function?
From the list of X to X.
Right, so we just look at this. This is the input. And then the output will be this is X. For Scala, it's not exactly that fun because most of the things are already declared. Okay? For Haskell, this question is harder because it's not declared. You need to infer. This is the input argument. This is the output. So, but there is still something that is slightly different here. When we talk about Scala in comparison to the Haskell, is that the function is not automatically carried. So if I have this, and then I say I accept another one, ys like this, then in Haskell it will be something like this. Because you automatically carry every function. Let me increase. But here in Scala you have two kinds of groupings. One is that the non-carried grouping, like this. So this will become comma. Basically, you need to get two lists. You definitely have to get two lists. And the other one is that the carrying is actually done using this. Separate input argument groups. Okay, so we did this before in the lecture. If you only supply xs, the result will be a function that accepts ys. So then you can do carrying. So for this kind of syntax, what you will have is then the standard typing, like this. All right. So there's a slight difference. Okay, so and to test that this one actually is different, you can check that the way to call is actually also different. Okay, so this one you have to give the other one explicitly, like this. For this, you have to give it like this. It's a different way of invoking the function. Okay, so any questions? So the changes for question 3 is that, so instead of throwing an error, we want to use the option class. The option class is a functor, if you remember, but this can be implemented as a case class. And again, the advantage of using this as a case class is that you can do the pattern matching on the type. So the only difference here is that almost everything will be the same. So you can just copy paste this one. Almost. Okay, so if you copy paste this, now you just have to match everything into the option type. Okay, so this is one possible implementation of an option class. You have the sum and none. So for this particular one, then there is sum. For this one, there's none. And for this one, just call it correct. Right? This one actually forget whether it should be this or this. But I think this one should be okay because we have the nil as well. It's a slight changes. But now here you don't have the error. You don't have to throw the exception. But we can get none as the output. Let's comment this and uncomment this. So if you run this again for question 3, this is what you get. So sum 3, sum 1, and none. Okay. So nothing major here. It's just that I want to introduce you to the notion of the option class in Scala. Okay.
Can say it's similar to the maybe type in Haskell,
Yes.
right?
The option is basically maybe type. function 4 is something. So I assume all of you know some algorithm, right? So there's this thing called the insertion sort, and the way insertion sort works is you basically take one element and you insert it. It's like you're sorting a card on your hand. Just pick one and then just insert. Keep on inserting. We do have this insert function. The insert function will basically insert it at the correct place. If x is smaller than y, so x is what you want to insert. If what you want to insert is smaller than or equals to the y, then you just insert it in front. Okay, otherwise you try to insert behind. So you start from the left, you find whether you can solve it. So the way the sort works is then you keep on going to insert things into, you divide. So insertion sort works like this. So this is, you have your original stack, you split it into two parts. This is the sorted subcomponents. This is the unsorted subcomponents. So this sorted part starts with empty. So what you do is you take one of this element, you put it here, such a way that you still maintain the sortedness. And then the one that is unsorted is reduced by 1. Okay, so you use the insert method here to maintain that the sorted subset is still sorted. Okay, so the unsorted component will just decrease by 1. So what are the cases? Match. It's the usual one, case nil. And then a case that there are something here. Okay? When it's nil, you create a new list. When it's non-nil, so you return a new list. So let me see. I did this last week, so I kind of forget the answer. If you do not want to create the two lists inside our arguments, so our arguments only takes in one, right? So the simplest algorithm is basically just to have another function that takes in both arguments. Then you just keep on expanding this while reducing this. If you do not want to create a new function, then what we do is we insert x into something that is already sorted. So we sort this xs. Once this one is sorted, then if we insert this into the correct place, it will be sorted. Okay, so that's the main idea. So slightly different mechanism from here. So this is the general idea, but the way we implement it is that we look at this, make it smaller, right? So this is the unsorted. This is the unsorted region. Okay. Once you sort this, so you separate your list into the first component and the unsorted. The first component and the unsorted, the first component and the unsorted, until eventually you hit either 1 or 0. 1 is actually also trivially sorted, so you can actually have another case where it's just 1. But 0 is the easiest. So once it's empty, then this one is basically sorted now. So this one initially unsorted, you make it to be sorted. Once it's sorted, then you insert this at the correct location. And then you keep on doing that. So you cascade it back upwards. So there's a few test case here. This one should be 1, 2, 3, 4. If it's just one element, it's just 1. If it's empty, it will just be empty. Right? So again, Scala allows higher order functions. So if you are really forced to do if the first thing that comes to your mind is basically, well, I need 2 arguments. Then what you can do is you can define a function here. Function within a function. Right? Then you can call this function instead. So now we look at a tree. So first, the description of this tree. It is slightly different from the tree that you have learned, I believe. My leaf does not contain any value at all. All the values are contained in the node. So this is not a very efficient kind of tree. So if you want to have a tree, I have an example here. You have 1, you have 2 here, and you have 3. So this one is nothing. This one is also nothing. So I allow this kind of tree, but at the expense that this one has to be nothing and nothing. So this one is the leaf. All the empties are the leaves. All the values are stored in the middle. Okay? I believe what Prof. Chin had before was that the leaf itself is a value, contains a value without any subtree. So the other possible shape for the tree is actually that the leaf here contains the value. Right? But this one means that there must be a link here. So you cannot have this kind of tree. Okay? What I want to do is I want to allow this kind of tree, so I need to be able to make the leaf to contain no value at all. It's just a slight modification. The disadvantage is that now it's longer to describe the tree. Okay, so this is the node. Okay, the value is 1. The left one is a node. The right one is a node. This node. The right one is a leaf. Okay, it's far apart there. If I want to make it look nicer, this is the value. This is the left, this is the right. And then this one is this, the value, the left, and the right. Okay? So I have 1 where the left one is a node and the right one is a leaf. And then 2 here, the left one is a leaf, the right one is a node of 3, and then the left one is empty and empty. Okay, so how do I find the maximum value? What is the maximum value inside the leaf?
No.
So again, this one really depends on what your integer is. You can look at the smallest value of integer, because any other value is definitely going to be larger than this. Or if you make a restriction that there's no value is 0, then just say 0. You assume that it's always positive. So this is now just 0. Okay? For this part, when there is a node, you have a value. You may not have a left and a right, but you still need to go through there. So you need to find the maximum between three values. So it's either V is the maximum, or you go to the left and there is a L is the maximum, or you go to the right and there's a maximum value there. There's a maximum, then you need to find the maximum between these three components. So you can do a lot of if else. The hint here is use list.max function. So list.max will find the maximum within a list. You need to make this to be a list of three elements. So list.max. Okay. So this is the finding the maximum. So the maximum here is basically either this value or whatever maximum I can find here, or whatever maximum I can find here. Let me show you the other shape of the tree here is more complex. I have 1, 2, 3. There's 5 here, which is 4 and 0. And again, it's much longer to implement. And I forgot to do this. Okay, so I get the maximum 3, 5, and 0. 3 comes from, this is 3, the 3 comes from here. The 5 is from here. So this one is the maximum here. When you compare 5, 4, and 0, so that's the maximum. This one, you compare 2 and 3, you get 3 over here. The maximum here is 3, the maximum here is 5, so then you compare 1, 3, and 5. Then you get 5. For empty is just 0. Okay, so flattening a tree. So flattening a tree, for this one, you have, there's two possibilities. This one is called the infix, and the other one is a prefix. So infix is you go to the left first, left, your own, right. Okay, so that's infix. And why is it called infix? That is because if you represent the arithmetic operation as a tree, what you have is plus. Let's say this is multiply 2, 3. So 2 times 3 plus 4. So let's say this is your tree, right? This is why it's called infix. The infix notation of this is that you get 2 here, you go down first, you get 2, and you go up here, you get multiply, you go down, you get 3, you go up again, you get plus, you go down, you get 4, and then you're dead. For arithmetic operation, then this one is actually, you can do the bracketing. So this is about the same, but we need to put this into a list. So the list corresponding to this will be just 2 times 3 plus 4. The essence is the same. The essence of the algorithm is the same. There is the list concatenation operation, and it's just a plus plus. So if you can get the list on the left, the list in the center, and the list on the right, then you just concatenate all of them. So again, tree, match, case, leaf, case, node, VLR. For this one, yeah, I didn't really say anything. But for the leaf, you don't put anything based on the example here. You're not going to even put 0. So this is just nil or empty list. Now when you have this, then you can look at 3 possible values. This is a list somewhere in the middle. This is a list. This is a list. You need to convert that into a list. We go to the left one first, so you have infix left, and then you need to make V to be a list. So you just put it in this constructor. Then you need to go into the right one here. And then in between just concatenate. Alright? Okay, so if you run this, should be correct. Okay, so you get 213 for that. You go 2 here, and then you try to go here. So this is nothing. 2, 3, and then 1. You get 2, 3, 1. So again for this, you try to go down. There's nothing here, so you go back. You get 2, then you get 3. You go up 1, 5. You skip 5 first, so you go 4, 5, 0. 2, 3, 1, 4, 5, 0. Okay, so any questions so far? For the prefix, then the only difference will be the ordering of this. Okay? So if you can find a general structure to concatenate list for the traversal, the only thing that will be different will be this part, the order of this operation. And that's it.
Sorry, can you repeat the order again? 2, 3, 1. First example.
Okay, so this one, right? For the infix, you try to go here. Okay, because always go to the left one first. But the left one returns you nothing. And then you go back here, you look at your value, so you get 2. And then you look at your right. Okay, so from here, you actually have to go leave here, nothing, 3, nothing. So you get 2 and 3. Okay, and then you go up again. And you look at this guy. So the full traversal will actually go like this. You have 1, you have 2 here, you have nothing, you have 3, you have nothing, you have nothing, you have nothing. So in the traversal you get this. So this one is nothing. So you get empty list. Then you go up here, you get 2. Then here you go here, you get nothing again. Then you come here, you get 3, nothing. And then here is 1, and then you end with nothing. Right? So the concatenation of all this is just 2, 3, 1. A similar thing for this, but it's much longer. For the prefix, you need to print your own first. You need to put your own value into the list, followed by the left and the right. Okay, so we use the same tree here. You start from here, so you put 1. You come here, you put 2 first. Then you come here, you put nothing. Then you go back. Oh, I already put here, so then I just go here. And I put 3. Then I come here, nothing. I already put this, so I can go to the right, nothing. I already put this, so I can go to the right, and there's nothing, and then I go up. Alright, so that's prefix. You concatenate your own first, followed by whatever on the left and whatever on the right. Okay, so let's try to do this one more time with this more complex one. So I asked to give you an idea. So you have 1 here, and then you have 2, nothing, 3, 5, 4, 0. Okay, so you start with this. Okay, so that's 1. And then you come here, 2, nothing. I already put this, then 3. Go up. Oh, I already put this. Now I'm putting this 5. Go down. There's 4. This one already done, so I go 0, and then go up again. Yeah. 2, 3, 5, 4, 0. Uncomment this. So the only difference here is that the list V must come first. And the rest is the same. Okay? So if you want, you can then try to parameterize this. Okay? Because the fact is that this is just an operation. This is the operation that you do once you get 3 values. To parameterize this, you can have a single traversal algorithm. The only thing that you need to do is how you can combine the rest. You have a function that accepts 3 arguments, and then how you do it is it depends on how you want to order this. If you want to abstract this out, you can always have a combiner, which is a function that accepts 3 arguments and return a new list. Then you can just say combiner or something. Then now you have a single function, which is traversal, that can do infix, prefix, or postfix. I don't have postfix here, but if you want postfix, you can also do postfix. Yes, that's already uncommented. So now you will get that. So 1, 2, 3, 1, 2, 3. Should be 5, 4, 0.
Correct. With 0.
But this one is 4, 5, 0. Let me arrange this. There might be one, 2, 3, 5, 4, 0. Oh, yes. Prefix.
It's not the infix. It's copy.
You should not copy paste fully. Okay, so now this one is correct. Okay. It will be much easier if you have the traversal function itself. Each individual type of traversal. Now this one was slightly modified from the lecture. I think this one is exactly the one in the lecture, the structure in the lecture. You have a variable which contains the name, you have a function which has the argument, which is a string, so only a single argument, and the body. You have the function application, which the left side should be a function and the right side should be the whatever it is you want to apply. Right, so the meaning of this should be the function v var should be some kind of lambda that contains v and dot x. Okay, so it's lambda v dot x. It's just a function. If we apply this to something like y here, the result of this will be just x. Okay, so that's the lambda calculus part. For this one, you have lambda x dot x. Now you can see here that the x here is bounded. It's bounded here. It's not a free variable. X here is a free variable. It's not bounded. X here is a bound variable. It's bounded to that x.
What was the difference between v dot x and x dot x? It's
The difference will be in the function application like this, it's not returns x. Whatever x is. Here, it returns y. Because it accepts an argument x, and then it returns that x. You have substitution, every x will be replaced by y. Okay, so bound variable you can always substitute. Free variable you cannot substitute. So now here, this is something that is more complex. We have x to x, divided by x. The x here, there are two x. One is this x, that is bounded here. The other one is this x, that is not bounded anywhere here. Okay? So if you want to differentiate, there's x1 here, there's x2. x2 is unbounded, it's a free variable, x1 is bounded. So we need to be able to give all the free variables. So if I give this, I should get x as a free variable. If I give this, I should get nothing. Or actually, if I give this. Okay. If I give this, I should get x again. And there's a hint. Use either filter or filter not function. So if you have a list, you can filter out the elements in the list based on a certain property. So that's what we're going to do. So as you see from the theme of this tutorial, the pattern matching will match exactly the term. So you have all of this. You have variable, function, and application. So if it's var, then you have some x. If it's function, you have x and the body. If you have function application, you have the f and the v. Okay? So then all you have to do is figure out what will happen on all these three cases. The easiest one will be, well, I'm not sure where this x is, but if I encounter an x, I can always assume that it will be free. Okay? So unless it's bounded, I can always assume that everything is free. So then I can just return a list of x. Now, when I have a function, anything that is within this x is bounded. Okay? So I need to be able to remove this element out of everything that I find. So first let me try to find what will be my potential free variables. So my potential free variable will be if I do a free vars on the body. And this is my potential free variables. It is a list of strings. Then all I have to do is remove all x here. And to do that, then you can do the filter not. Or you can do filter. You basically only want to keep everything that is not equal to x. So you filter not x equals to. Yeah, so that's how to do this. You need to give a function, right? So y. This is a function. This is the lambda term. It takes one argument y, and you say the x is equals to what? You remove everything that is equivalent to x. Then for function application, what you have is f and then v. Okay, so f, you just concatenate this. F, v. Okay, so this one is pretty straightforward because these are the terms, and everything that is free here plus everything that is free here. This part is the hardest part. Okay, so whatever you found in the body, if they are not bounded here, then they are free. Okay, so this one is x empty x. Yes, I forgot the case. Yeah, so don't forget the case here. You match with this particular case. Okay, so you get x, empty, and x. Right, so any questions here? The last question, question 9, has two different parts. What I want to show you here is that the structure, once you get that structure, the structure remains the same, regardless of whether you are doing a compilation or you are doing an evaluation. Okay, so this is just trying to show you the similarities between the first one here is a compilation, the second one here is an evaluation. Okay, so you get an arithmetic formula of some form. Let's say this is your programming language. You compile it to something else. Okay, so that's compilation, right? You have in compilation of a program, you have your original program. The output is another program in a different programming language. And that programming language can be your machine language. For evaluation, you have a program. If you evaluate it based on a certain input, what you get is just a single value. Right? So this is the single value when you evaluate all this. And then you will see that the structure is actually exactly the same. There's almost no changes in the two code. So when you want to print the arithmetic here, this is just your infix. Your infix traversal just now. So I have expression, match, case, value, and case add, left and right, case multiply, left and right. If it is n, then you just convert this to string. Okay. For this one, then you need to print the left and then you need to print the right. And in the middle you print the plus. Okay, so you have print arith left plus print arith r. Okay, and then if you want, you probably need to print the closing and opening bracket. And then this one is also the same. You do this, but you print the multiplication. Okay, so let me show you the print first. Actually, print needs to go hand in hand with the evaluation. So let me show you the evaluation. The only difference here is that instead of returning a string, you need to return a value. So this one, simple. You don't have to return the string. So now this one, these two cases, these four sub cases, will be just evaluate. The plus here will be taken out of its string. So you get this. And then you don't even need, or you can also take this out of its string. And then the same. So all you have to do is take that evaluation out of the string. Okay. So notice that the two codes are almost exactly the same, except that this one you put strings everywhere. If I commented out. Okay. So that's the result. Okay. Here on the left side, I have compilation. On the right side, I have evaluation, or what we actually call as an interpretation. So the structure will remain the same, but the code produces two different things. So this is one of the advantage of functional programming, because when you see these two codes, you will immediately see that this notation is exactly the same as this interpretation. And this gives the meaning to this format. Okay? Alright, so any questions? If there's no questions, then let's take a quick break first. Let's come back at 7:30.
Question on the bounded and unbounded variable. Can you explain it?
The bounded and unbounded, which is this one, right?
Yeah. Bx and xx.
Okay, so this is in a lambda calculus. So you have a lambda here, x, x. This x is bounded by this. And the reason why it is bounded is because it's basically the scoping. This x covers this. That means if I want to replace this x, everything that is bounded is replaced. Everything that is unbounded, everything that is free, cannot be replaced at all. So this is function application. When I do, so this one is a function, this one is the term, v. So I need to put v here inside the f, and this value will replace any x that is bounded here. So in this particular one, this is the only x that is bounded. If there's another x that is unbounded by this, then that x cannot be replaced.
What do you mean?
Right, so let's see if I can find an example. So you have lambda, let me make it bigger. So you have lambda v dot x or let's do this. Lambda x, and then this is the first function application. This is the second function application. So this is not the correct syntax. This is not a correct program, but it is one possible program, right? So let's say I want to do this outer function application first. So this y will try to look inside and then gives me everything that is bounded. I will replace it with y. But there's nothing bounded here, okay? Because I'm looking at this as a single term, and this one is a x. This x is unbounded, so I cannot replace this x with y. Okay. So bounded means that this x is attached to a lambda, and so if I'm using it to replace something, it's only this x that is attached to this lambda, not any other x. This x is not attached to any lambda, unless I have this. So let's make it something more complex. So x, lambda x dot lambda x dot x y. Okay, for this particular instance, this x is bounded by this x. Okay? Because this x is attached to this lambda, and this is still within the scope. This x is bounded by this x. Even though we have 2x, the bounding is different. So when I look at this y, well, then the only thing I can do is I can only replace this, and based on the bounding of this x, I must replace all the occurrences of this x with y. So I cannot replace this, because this x is not bounded by this. So I can only replace this. After I do the substitution, what I will get is lambda x of x, y. this outer ones is gone. This already replaced this x is replaced with y. So this one goes here, and this goes here. So now I can proceed further. I can proceed saying that, well, this y must replace this. And then I get this replaced with y, so I get y.
What are the syntax of
The lambda.
dot dot dot?
Oh, dot means if you define a function, right? So let's say you have function x. The dot is basically just this.
Oh, okay.
Yeah, this is basically the whatever this is. After the dot is the body of the function.
Oh, after the
Okay. And it's also the same when you look at a formula. It's also the same. So you have for all x dot. This is the body of the formula. But instead of a lambda, you have the for all. You have that exists. Something. Okay. So the dot is just to signify that this is the all the variables. This is the body.
Okay. So can we open bracket x plus 1 after the dot?
Yeah.
Like that.
And if it's unambiguous, then you don't even need the bracket. You can do this. If it's unambiguous.
Yes. Can you explain with the examples the 3 lines of printing and v dot x and the 3? They show you a list of x.
Which one?
Just this question test Q8. Yeah, these 3 examples.
This one?
No, just below because this is what's shown on the screen, the print line. Print line, free variables.
So which one is it? This one?
Yeah, all these are printed on the screen, on the console when it runs.
Yes.
Can you explain the x and then vx? It's just some string you put it into.
This one?
Yeah,
Yeah, it's just any name.
but it's showing something like the x dot x.
Not really this, but if you do the print term, so if I uncomment this, you will see the output of the print term.
Oh,
The print term is the one that we kind of use in the lecture.
It takes in more than 1 term to
Because of the currying, right? This one is already universal enough.
can't use lambda x, y, plus.
You can, but it complicates the formula. It complicates the notation. And because of currying, this is actually enough. Taking in 1 argument is actually enough. You can simulate any kind of program if you use currying. So that's why typically for lambda calculus, this is just 1 variable. Because for the rest, you can use currying to simulate the other ones. Yeah, so this is going to be the output.
okay.
But I just removed the bracket left and right. The slash here is just basically your lambda, but there's no lambda in my keyboard. Okay, so any other questions? Yes.
Can I give you an expression in Haskell? It's also lambda expression, and you convert into the non-curry form. Because I usually we do something like slash x space y gives you x plus y. Then how do you write the non-curry version?
In the lambda calculus?
Yeah.
So for the lambda calculus, then you have to first the extension of the lambda calculus to allow for a non-curry form means that you must have this general formula where this one is a vector dot something. So then you can have x comma y, x plus y. Okay? But then you have to be able to differentiate between this and just a single a current application. Okay, so now you have to give the notion of a vector. So if you want to apply this function, then you need to apply it to a vector 1, 2. Okay. And it basically just complicates the notation itself. The power of this program, whatever this program can compute, is exactly the same as the lambda calculus with only a single argument because of array. I mean, you can always make it general like this. It's a vector. So now, function application is a f. V is a vector. Right? But obviously for this, the notion of a bound and free variable again needs to be changed slightly. So this y here is also bounded. But if I put z over here, this z is unbounded, following the same reasoning. Okay, so any other questions? So that's lambda calculus. In principle, nobody writes lambda calculus anymore. I mean, you know Haskell is you don't really write it as a lambda calculus. Because first, yeah, I mean there's a conversion, but the thing is you don't have lambda, and then you don't have to write brackets everywhere. Sometimes the bracket is just meant to be, it's clear from the context of the bracket. For a true lambda calculus, every application must end with a bracket. Then you have basically lots of brackets. For any reasonable size program, at the end you will always end with a list of brackets. There is actually a language that is still very, very close to the lambda calculus, and that's called Lisp. So, yeah, so there's Lisp. With one of the possible flavors called scheme. So if you want to know whether someone is writing a Lisp or a scheme program, just look at the last few characters. If they're all close bracket, it's definitely a Lisp. So where were we? Negation is a failure. Okay. Oh, we haven't done the cut yet, right? Okay, so let's backtrack to this one first. Negation is a failure. So in Prolog, we have this closed world assumption. Basically, everything that cannot be proven is treated as a false. So what it means is that any form, you only have two possible outcomes. Either it's true or false. If you have exhausted all the possibility, it's true. Right? If you have exhausted all the possibility and you cannot find, then that's false. Right? Okay, so if you found a path to that, it's true. If you have exhausted all the possibilities and you cannot find any possible match, that's false. Okay, so that's the basic assumption here. So if you want to know who is not the father, whether this guy is not the father, then this one is true because you cannot find You cannot find this mapping where you have John and Carrie. So father John is Mary. John is the father of Mary. John is the father of Tom. John is not the father of Carrie because there is no such fact embedded in this program. And this brings us to some advantage where you can say that all the males are everyone that is not a female. So you only have to define one set of facts. So if you look at it in terms of a set here, this is the set of female. The one outside is the negation, that will be the set of male. Okay, so that's in terms of a set. The closed world assumption means that you can describe the universe. Everything inside the universe will be described. Okay, and this brings us to some possible weirdness where because we are doing backtracking, if this one is true, then we do this. But once we're done, we give out one answer, and then we do the backtracking, we try this. When we are trying this, we again do exactly the same thing, and then we get 1, 1, 2. Okay? So this has a certain kind of weird property. Because the backtracking means that when we try to search this T, it need not be within the R, or within the H need not appear inside T. Okay, the selection here means that H appears inside T. Right, so when we want to remove duplicates, we do not have this condition, so it can be true or it can be false when we do the backtracking. So if you try to get all the values from the backtracking, you try to remove duplicate of 1, 1, 2. This is the choice number 2. If you go into the choice number 2, what it means is that, well, 1 is inside here. Okay? So the H is 1. The remaining tail is the list 1, 2. Based on the property of this relation, 1 is inside here. So this one is true. So you can traverse this. Okay, but if you traverse this, okay, so this one is true, then you need to remove duplicate from here. That gives you 1, 2. Okay, eventually that will give you 1, 2. But on the other hand, after you do the backtracking, so after you get this one as an answer, you go back here. This is the other option that you have not considered. It may still give you an answer, so you try to come here. But when you try to come here, you do not have this guard. Because you do not have this guard, then it doesn't matter whether this guard is true or not. So what you have is that, well, yeah, I tried to just remove the duplicates from the 1, 1, 2. So X here still contains 1, and then you try to remove duplicates from here. So at the end, you accumulate, you get 1, 1, 2, which is nothing removed. Okay? So to safeguard against this, based on the closed world assumption, what we can do is we can put the negation of this. Right? So that's what we did last week. So not selection HT, which is this. So now, based on these two guards, either this one is executed or this one is executed. Both cannot be executed at the same time. Okay? And if you look at the backtracking tree, then what you get is this one prevents this from being executed because this results in a fail. Right? And the reason why this one results in a fail is because this particular one, checking whether 1 is inside the list 1, 2, returns true. So this part returns true. Because you say not, it will fail. Alright? There is another way to do this, and that is using cut. Now cut is something special. What cut says is basically that you still look at each of the relation from left to right. Okay? if this one is successful, and then you encounter a cut, when this one fails, you will not backtrack to this. You will not backtrack beyond the cut. If it fails, it just fails. Okay? But when you want to remove duplicates, again, this one will never fail. So, but again, there is still that notion that once you go through the cut, you will not do backtracking beyond this cut. You will just stop. So in general, what you have is this. So let's say I have a relation R, then let's just give it X. So if I say that this is doing some relation 1, X, and then I cut, then I have relation 2 with X again, relation 3 with X. This is just a simplified example. The backtracking will be things like, so well, if this one passes, then I go through this, I encounter a cut, and then I look at this. If this one fails, I will not go here, and I will not backtrack. If this one passes, then I will look at this. If this one fails, then I will backtrack here. I will look at the different options for this. Okay? But once this one fails again, then I will not backtrack here. I will not backtrack beyond the cut to anything before the cut.
Means if you add in another relation below this one.
Yeah, so R here, if it fails, I will not look at this R. But R2 has two different possibilities, right? So this is the A and the B. If I look at A and it fails, I can still look at B. Because I can do backtracking here. I can do backtracking over here. I cannot, but once this one passes through the cut, if all of this fails, I will not go backtracking over here. Or I will not do backtracking over here as well. Okay? So now the third attempt here is that, well, I can just put a cut here. If this one is successful, I will not even do this. Because I will not go backtracking beyond the cut. So let me show you. I forgot which website I used. Oh, SYI Prolog. SWI Prolog. No. Swish. Let's here. So this is the last remove duplicate with the cut. So if I say remove duplicate 112R, and notice that there's no next answer because I will not even do backtracking at all. Cut is good if you know that there's only one answer, and this gives you the first answer. For Prolog, we don't typically care about efficiency. If you care about efficiency, then you need to use cut in the correct places. So I think the most common example will be, how do you do a sorting? What is a property of a sorted list? So there's this very simple notion. So if you can define what is a permutation. So permutate. List X is a permutation of list Y if it satisfies some property, right? So let's say you can define that. And then so let's put question mark here first. Then you can say what is a sorted X. or just X is sorted. X is sorted if there's some property of sorted, right? So each of the elements must be in the correct order. So sorting. So X is the sorting of what? So Y is the sorting version of X if you can permutate X to get Y, and Y is sorted. Okay. The more efficient, so this one is very, very inefficient because finding a permutation is typically very hard. And then after that, you need to check whether it's sorted. And then even after that, you need to backtrack it. So you will get all the possible permutation. So the more efficient way for this is, well, basically just say that it's sorted, Y is sorted. Once I find this, I cut. Then I say that it must be a permutation of this. Right? So now I will only get one answer, and it satisfies both. And it's guaranteed to be sorted. Okay? So the advantage of Prolog over any other programming language is that you can just describe what you want to find. The algorithm for finding this is handled by the resolution and what's the other one? Resolution unification algorithm. Right? But again, if you compare to the insertion sort that we did with Scala before, this is extremely inefficient. Because at the worst case, you need to find all the possible permutations. So yeah. But again, this is one of the simplest form of sorting. Because you know that it's sorted and you know there is a permutation of method. Okay, so this is the resolution, the search tree. So once this one is successful, you will not even backtrack beyond this anymore. So that's why the right part of the tree is not going to be executed at all. Okay. Like many other functional programming, Prolog is typically a pure language. You don't have assignment, you don't have anything. But there is always this impure feature. Because what is a language without the impure feature? Right? It's typically not a very usable language. So in the impure Prolog is that you have this, all of this, but there are two states of every variable has two possible states, whether it's bounded or whether it's unbounded. Now here is a different kind of bounded thing. When you, let's put an example here. So let's put a very simple Rx. Let's say it's only defined in terms of R1 x. So the relation R is defined in terms of relation R1. There are a few points in this program. So if this one starts as a variable, then at this point, it is unbounded. X is unbounded. Now, once you finish doing this, if this results in an answer, so let's say there's an answer x equals to 2, then at this point, x is bounded. Okay? So that's why this is impure. Because when you ask for atom, x, if you ask before, this will say that, well, this is unbounded. If you ask after, it will be bounded. So the predicate atom, the result of this depends on where you are using it. So let's see, I think I have an example. Nope. Or is it here? Okay, let's take this. So I have parent, father, brother, son. Here, write atom x. Okay. And then I can say that, well, write atom X. This should be capital X. His son. Who is the son of who? Tom. John. I think atom is but if I don't write this, okay. Hey, this so I'm just going to write X here. I'm just going to write X over here. Oh right, because this is who is the son of John? Okay, so look at this. The first print comes from the fact that it comes before finding all the males. So at this point, X is unbounded. It's a variable. It's just got a renaming. It's renamed to some number 4566. And afterwards, after you finish finding the male, then this value of X is bounded to John. Okay, in this case, it's because John is the first male predicate here. The first male relation here. So we just look for John. And then this right will give you John. Okay, so that's why it's impure. The first right give you a variable. The second right give you John. The third right give you Kevin. Alright? Now, this is because of the backtracking that you go into Kevin. It's not because of. So you backtrack on this male. After you find John, then you after you find John here, then you backtrack. I want to find another answer. You get the next male, which is Kevin, and then you grab. Yes. But it's impure because the first one and the second, right? Even though it's on the same variable, it gives you the different output. So the same will be for atom and var and atom, var, and integer. Okay? The result of this depends on where you put it. Okay, so let's go into the constraint solving part. This is the part that is fun because you can use it to solve puzzle. The downside is that the last puzzle, the 5 houses, I couldn't run it to completion. The search space is so big. So to do a constraint solving, the easiest way will be we put everything into numbers, right? Because it is easy to deal with numbers. You can still run the unification algorithm and the resolution algorithm, but number is infinite. So how do you deal with it? You cannot simply enumerate all the possibilities, right? So there's this technique from CLP, which is constraint logic problem or constraint logic program. Remember this resolution. This one is dealing with list, right? If we deal with something else, let's say that some relation x here that depends on some relation 1x, you can kind of write this resolution tree. So R here depends on R1, and so let's say R2 here. So it depends on this and so on, right? And at each point in the program here, you can find the bound of x. We start with some simple bound that is from -infinity to infinity. Okay? And let's say to go here, the R1, it must satisfy that all the value of x must be greater than or equals to 5. Okay? Then you propagate that bound well, it cannot be minus infinity because this one say the x must be greater than 5. So from here you find that, well, it must be between 5 and infinity. Yeah, and then you propagate again. Well, this one says that x must be smaller than or equals to 102. Okay, so from here you propagate again. Well, then if I need to satisfy this, then I have to say that it's between 5 and 102. So that's the essence of this integer bounding. There is a possibility that you get no solution, because if I say that this one must be smaller than 2, there is no possible bound for this. Then you get it's always a fail. But if you have a probable bound here, that means any value of x between these two values, between these two extremes, will satisfy this R. Okay? So that's the essence of the constraint logic programming. And you can use it to solve puzzles. Remember the is operator. Like x is x plus 1, or x is 1 plus 2. Right? Because whatever on the right hand side of is cannot be a variable. So it's kind of like an assignment. Now here, we have a generalization of it, where you have the hex equals. Whatever on the right can contain variable, whatever on the left can also contain variable. You will try to equate this based on the bounding property such that you satisfy the equation. For this particular one, then the bounding is simply just, there's only one value of x. The bound is between 3 and 3. Otherwise, it will not satisfy this. Alright? So if you look at this, x is greater than 4. So almost all the operations are the standard arithmetic operation, but it is preceded with a hex. So here is where you see the boundedness in action. X is greater than 3, so it's between 4, and sub here is plus infinity. So if you say that x cannot be 10, so x is not equal to 10, then it can be from minus infinity to 9, or from 11 to plus infinity. You just basically remove 10. You get 2 disjoint set. And this one, the square of it is equal to 9, so you either get 3 or minus 3. Okay, so simple equations. Remember the factorial function? The factorial function, we can now write it in a way that we can search what is the value of n that produces 120. Because unlike the is operation, the is operation, the right hand side cannot be a number, cannot be a variable. This hex equal, the right hand side can contain variables. This more advanced constraint is basically directly lifted from the constraint programming. You can always write this, you can always write all different here in another way. But the reason why they have all different is because they can implement it very, very efficiently. The other way to write all different is that you have a list containing x, y, z. Okay, so let's say you have a list. You have a list here containing x, y, z. To say all different, then you can also say that x not equals to y, and y not equals to z, and x not equals to z. Right? So now you can see that if you add more variables, the size of this increases. If you have 4, okay, if you have 4, it's not simply 4 formula here, because you need to say that w is not equals to x, w is not equals to y, and w is not equals to z. Okay? So the exact number of this inequality is basically n times n, either plus or minus, I think plus 1. over 2. Minus. Oh, plus. Wait. Yes. Oh, minus. If it's 1, it's 0. Okay. So if it's 2, it's 1. And so, yeah. So this is the exact number of inequality that you need to put. So that's why it is easier if I just say that it's all different. VS. Everything in VS are all different numbers. Okay, and the reason why this is an advantage is that, well, if you say that this one is, all the element here is within 0 to 2, then there's no answer. Without even enumerating anything, there's no answer. Because you have 4 elements, you only have 3 possible values. Okay, so if you want to specify the range, so notice here, the range is the x is within this range, right? So the keyword is in, if it's a single variable. If it's a list, it's ins. So all the elements inside VS is within 1 to 3. So you have x within 1 to 3, y within 1 to 3, z within 1 to 3. You just write ends. Just write the s there. This one is not arithmetic, but it's Boolean. This is the Boolean operation. Is the if and only if. Okay. So this one, x equals to y, if and only if b is true. B must be a Boolean. And the Boolean here will be either 0 or 1. 0 is false, 1 is true. And if you look at this, x equals to y if and only if b, well, x and y have disjoint set. They can never be equals. And that's why b is 0, because b can never be equal. These two can never be equal. Alright? If you make it overlap, so x is between 0 and 4, y is between 4 and 5, then there's a possibility that they become equal. Right? So b is no longer 0, b can be 1. So it's either 0 or 1. But you do not know which one is which. Just know that b is between 0 and 1. Okay, so let me show you. When you start with the switch here, at the start we are given 2 possible or 3 possible choice. You want to build a program based on the CLP profile. So you choose this. And then now you have all the library needed. So let's put this one, x. Actually, I can just put it equals to y, if and only if b, and then x in 0 to 3, y in 4 to 5. Okay, b is false. B can never be x and y can never be equal. If you allow them to overlap, then there's a possibility that b is actually equal. There's a 1 here. And they are only equal exactly when x equals to 4 and y equals to 4. Okay. So this is the factorial function that I told you that you can now use it to find what is the number n that makes n factorial equals to 120. So let me put c fact here. So previously, we just do this, right? Now, we use the constraint programming. And then instead of is, we do m. Okay? So this will use the library for the constraint programming. It will propagate the bound until either the bound is empty, then you get no solution, or you get the bound is just one value, then that is the possible solution. R n times R 1, and then C fact M R1. Okay, so the normal use is 5R. R is just 120. Next 10 is just false. This one is 120. Now you can find N. Previously we cannot do this. Okay, so let me write the old factorial program here without the this one is equal. This is good. R1 is, I think R1 should be after this. Because is means that it must be N times R1. Okay? So this one is okay, but 120 N gives you an error. Because one of this is still, N here is still not that one, this one. N here is still a variable. Either this or this. One of this is still a variable. Okay, so that's the advantage of the constraint programming. And this is where the puzzle comes in. So do you all know this puzzle? The send more money puzzle. So basically, what you have to do is find an assignment of what is S, E, N, D, and all this, such that this equality is true. Okay? So pretty simple. Well, actually not exactly simple, but if you want to do it yourself, then you just have to try to find an assignment of what is S, what is E, what is N, and then just check whether it's correct or not. Okay, that can be quite complicated. So the constraint logic programming methodology is that you have S, you have the value of S here, start between 0 to 9, E start between 0 to 9, and so on, and then you try to bound this. So S cannot be 0, because okay, so S cannot be 0, M cannot be 0, because M is the most significant digit, S is also the most significant digit, so it cannot be 0. Then you keep on reducing the bound, until eventually you get that this value is a single value. And then you get the answer such as this. So how do we solve this? So I can simply write everything here. I can have all my variable Vs as send more, so E is already there, M is already there, 0 is already there, so send more E. So send M-O-R-E, M-O-N-E-Y. Okay, so all the variables are there. Ints 0 to 9. Okay, and then how do I describe this? How do I describe this line? This is the hard one, right? So how do we form this number? Well, S must be in the 1000th component. S times 1000 plus E times 100 plus
Okay.
N times 10 plus D. Okay. Then you need to add the more. M times 100 plus O times 100 plus R times 10 plus E. And this should be equal send more equals to money. So this is money. So this one, this line is send, this is more, this is money. But for the money, this one is times 10,000, 1,000, 100 times 10 plus this. Right? Almost. But we also need to say that S cannot be 0. And M cannot be 0. Okay? Then all you have to do is just run this. Could be long. Oh, abort. One more thing that I forget. All different.
It can't all be 0.
Yes. I forgot how long this one takes. Okay, so let's continue this first. Hopefully we'll get an answer by then. So again, this is what I said. So these are all the variables. It's within 0 to 9, all difference. This is the send more. This send more money. Written in a nicer way. Okay? And then the last one is basically just saying that M cannot be 0, S cannot be 0, because you need the most significant digit. Yeah. Let me see if separating this actually makes some sense.
Wow, that's fast.
Okay. Now, so S here is 9. So we only found some of this. If you want to get the rest, so here the constraint solver already solved certain parts of it, and then it says, well, N is within this, E is within this, R is within this, Y is within this. If you wanna get all the answer, then you just need to say that, well, I need to label all of them. I need to give me an answer. For all the variable here, give me one value. So now you have this. This is the labeling of the send more rate that makes sense. Okay? So S is 9, E is 5, N is 6, D is 7, M is 1, O is 0, R is 8, Y is 2.
So is it we only give one permutation or all permutations?
This one can still get the next permutation. So you want to label everything, but apparently there's only one possible answer. Right? So this one, without the label, it will just try to satisfy the condition, all the condition first. It did not arrive at a single solution yet, because you do not force it to give me one answer. And at the very least, it says, well, yeah, it is satisfiable if I have this, this, and the rest is just within this. I know that there's an answer within here. And that's what it's just giving me. Because you're not forcing it to give me one exact solution. Label, just force it to have an exact solution. Good. Any other question? So this is the partial answer. So if you notice that this one is basically just this, but with the variable name is renamed. And yeah, so again, you can, if you use label, you can get this answer. But this one is more detailed because it has this. But for us, we do not have this relation. We just write everything here. So the labeling will just label the VS. And so easily solve this if there's time. So my current solution, it will run infinitely long. It's probably because I didn't really optimize it yet. But think about it this way. Okay, so you have 5 houses. So all you have to do is number the houses. The first house is 1, second house is 2, the third house is 3, the fourth house is 4, the fifth house is 5. Okay? So you look at the Norwegian lives in the first house. Okay? So then you have a variable called Norwegian, it's equals to 1. Because it lives in the first house. Okay? You have a variable called English. You have a variable called red. English equals to red. Okay? So basically it's just a list of all those. Spaniards equals to dog, coffee is equals to green, and so on. Now this one, greenhouse is immediately to the right of ivory house. Okay? So you have the greenhouse here. So this is on the right. This is ivory. If this one is n, this one is n plus 1. Okay, so that's the kind of relation you do. So ivory, or rather green, equals to ivory plus 1. Okay, you need to form this. Milk is driving the middle house, so milk is 3. The person who drives the fork lives in the house next to the owner of the fox. But you don't know whether it's left or right. So it's either plus 1 or minus 1. Okay? So you can use the absolute. The absolute value of fork minus fox is 1. So this takes care of the plus and the minus. Okay? So you just have to translate all of this into something like this. And this is the example of possible assignment. So if you do not want to do this, you can just say that you can just translate house 1 to 1, this one to 2, this one to 3 immediately. You don't even need to have that. Just describe all the variables. Okay? And this one is a list of lists. So now, when you append all, you create a list called all here, which is containing all the sublists, right? But it's flattened. And then this is why we want to do this, because everything is between 1 to 5. Okay? And all these sublists, each of the value within that sublist are all different. Okay? And this is the translation, so it's equal. So it's better to just use hex equals instead of the equals, so hex equals, so that propagates the bound. This is the part where I say the green is equals to ivory plus 1. The absolute value, because we do not know whether it's on the left or on the right. And yeah, then if you try to run this, hopefully within time, it will be solved. I think my problem is that I did not use enough hex. Let's try if I just put hex everywhere. So then it's basically the bounding. So this is a translation. This is Sam Mori. Let's see if we can get this to give us an answer. Nope. It's probably going to take very, very long. Okay, but technically, if you follow the program to completion, eventually you will get an answer. Right? So any questions?
What's the question trying to find?
Hmm? The assignment. Actually, this one was a common puzzle like 10 or 20 years ago. So it was, at least when I was in Indonesia, there was this newspaper article that gives us this. It says, you know, all the bullshit stuff like this one is invented by Einstein, and only 5% of the people can solve this. You know, it's all the standard nonsense. One of the questions is that, so they have all this assignment, and then the question is, who is the one who drinks something? Right? I forget which one it is.
So all interconnections.
Yes. So you need to find all of those, and then you need to find an assignment that makes sense that this is the guy who drinks. So yeah, there was the puzzle a long time ago. So I forgot what's the exact question. But yeah, it's involved all the standard nonsense. Okay, so any questions? Okay, so let's try to finish that run. So let's have a quick break. Let's come back at around 8:30. And we'll try to continue with the